On va sur une méthode de chat. On va sur Zoom, sur le truc. Si vous êtes d'accord, on peut essayer. Ah, peut-être.
Ça m'est égal. Ah, je vais avoir 5 minutes de plus.
Oui, oui. So, welcome everybody. I'm very happy to see all of you, to see all of you here. I will be short. This conference, 1 week ago, seemed to be very a mess, but we are here. So I can say the following. If everything will go smooth, remember that it is thanks to the organizer. If something goes wrong, don't forget that everything was planned. Okay, so it is a pleasure to introduce the first speaker of this conference, Claude Sabbah, of the Corporate Technique Paris, who will deliver a talk with title on coalescing singularities in isomonodromic deformation.
So thank you. So thank you, Giordano, for organizing this conference and for the invitation. So, as we say in French, à tout seigneur, tout honneur. I will speak about a theorem of Giordano, Cotti. So, a theorem of Cotti, Dubrovin and Dubrovin and Guzzetti. I found this result very, very nice, very clever, very interesting. And I would like to, well, first to make emphasis that this was really a nice result in the theory, and also give another way of approaching this result that goes back to results of Malgrange going back to, say, the 90s or even before. So let me state first the result. Explain. So we start with a connection. So first in Cn, so the space Cn, I take out the locus where two coordinates coincide. So delta is, so the coordinates are called T1 up to Tn. And delta is the union of hyperplanes Ti equals Tj for all I not equal to j. So it's a union of hyperplanes. And let me fix T naught. So it's a fixed point in Cn minus delta. And it corresponds to a diagonal matrix, lambda of T naught, which is the diagonal T naught 1, T naught n. So by definition, with distinct eigenvalues. Okay, and let me fix also some matrix A naught, any matrix, and consider on the the trivial bundle on the affine line, the meromorphic connection. So on the trivial bundle, so rank n bundle on A1, on the affine line. So it will have coordinate z. Okay, so the is a coordinate. And so the connection has a matrix. So the connection, say, let me call it nabla knot. So knot meaning that I fix some value of the point here. Nabla knot, do you see equals D, so the standard differential, plus the following connection matrix, which is lambda T naught divided by Z plus A naught dz over Z. Okay, so this is the connection we are interested in. And this connection has a pole of order 2 at Z equals 0 and a pole of order 1 at infinity. So a regular singularity at infinity. And because the eigenvalues are pairwise distinct, an irregular singularity at the origin. And so at the origin, we have a Stokes phenomenon. So we have Stokes matrices at the origin. And because the pole has order 2 and the eigenvalues are just pairwise distinct, we can represent the Stokes phenomenon by a pair of Stokes matrices. One upper triangular, if you like, and one lower triangular. Okay, so there is a famous theorem of Jimbo Niwa Ueno, and also another approach by Malgrange, which say the following, that we can deform, so there exists a neighborhood of T naught, so say simply, for simplicity, simply connected neighborhood of T naught in Cn minus delta. And yes, before I should say something here. We can write, let me make a remark here, it will be useful. Because the eigenvalues of lambda are pairwise distinct, we can write so the matrix, any matrix A naught, as its diagonal part. So this is diagonal part of A naught, plus a commutator with lambda at T naught, and some matrix R naught. Okay, and this matrix, for example, you can assume that the diagonal is identically 0. Okay, so let's write the matrix like this. So there exists a neighborhood and also a holomorphic matrix. So from this neighborhood, so holomorphic, so that the following connection is integrable and in fact defines an isomonodromic deformation of our original connection. So nabla with matrix D plus. So now we have a connection on the space of parameters times A1Z. Okay, so here the space of parameters. So here we'll have a point T inside of it. So the connection is minus D of lambda of T divided by Z. So it's a connection in many parameters. So we have Z and variable T. Okay, plus commutator of lambda of T, R of T, plus D naught dz over Z. and plus, yes, commutator d lambda of t r of t. So we have an explicit formula which looks like the original one, except we have made some perturbation by r. Okay, and so there exists such thing which is an integrable connection. Okay, so that's a famous theorem or consequence of a famous theorem of these people. And now let me explain flat, if you like, integrable or flat. Okay, so no curvature. Okay. Now let me. So this is nice. This is a generic situation away from the delta, this locus where the eigenvalues of lambda are pairwise distinct. Okay, now let me consider. So let me go to the theorem here. So now what happens when some, yes?
The d that appears inside is with respect to all the parameters.
Yes, yes, it's a connection in all the variables. Okay, so D is so we have a connection on a bundle, if you like, on a bundle on this space. Okay, trivial bundle on this space.
And when you differentiate d lambda over z, you differentiate lambda with respect to t, and you differentiate the z also.
Yes, yes. Okay. So here you only find the but in the first when you fix t, you just differentiate. So if t equals t naught, there is a minus sign here. You find the dz over z squared.
So these have the property that when you restrict to a constant t, then it coincides with the connection we started with when t is equal to t0.
Exactly, exactly. So you have this. So it's a deformation. It's the meaning of, in fact, the meaning of isomonodromic deformation here. Okay.
Thank you.
So now what happens when, let me fix some point in delta that these authors call a coalescing point. So TC now, not T naught. So TC, the point in delta, so where some of the coordinates may coincide. And so it corresponds to a partition of 1n as a union, this joint union of subsets I sub k, k from 1 to r. And in each subset, then the ti equals to tj. And conversely, for different subsets, they are distinct. Okay? This is the coalescing point. Okay, now the question is, so the theorem is the following. It is the following. Assume so T naught is in some neighborhood of some given coalescing point. So which means that the coordinates of T naught, say, gather, so near some given T sub C. So you have a bunch of points of T naught of pairwise distinct values for each k. Okay, so you may find one point for each k corresponding to Tc and various points around of it for T0. Okay. Assume we are given that and that this matrix that we found extends holomorphically on some neighborhood of this point. So instead of being only defined locally at T0, it is defined, in fact, locally around the whole point, the point, the coalescing point. Then the conclusion is that first, that on this neighborhood, the connection nabla that is here is formally, so formally mean with respect to the z variable. So after making everything formal with respect to z, but not with respect to t, formally equivalent to the connection, say, nabla hat, which has a very simple form. So nabla hat is simply, so d minus, so plus minus d lambda t divided by z. So that's the same first term. And for the second term, you just take d naught dz over z. So up to making things formal, so you can find a gauge transformation, a formal gauge transformation that replaces nabla with this nabla hat.
And the formula is analytic in T.
Yes, yes. So it is well defined at each point in this neighborhood. Okay. And second, which is really the nice, a nice property, assuming that, then for, well, at T naught, say, for example, there exists a representative or a pair of Stokes matrices at T naught. So let me call them S plus minus at T naught. So at T naught, we had an irregular singularity at z equals 0. So we have a pair of Stokes matrices. It depends on some choice. So this is why I say there exists a choice of a pair of Stokes matrices such that for any k from 1 to r, so recall that k was parameterizing the sets of coalescing values for any k, and for any pair ij in this coalescing part, so they correspond to a given coalescing property, and I not equal to j, then the ij and ji entries of this vanish. So if this theorem says that if we have a coalescing point, then it implies that in the neighborhood, the Stokes matrices cannot have ij entries corresponding to this coalescing point. Okay, so it's a strong constraint on the Stokes matrix, or if you like, it's a strong constraint in order to know whether this Jimbo, Miwa, Ueno, or Malgrange deformation can be extended up to the point. Okay, so a necessary condition is that this occurs. Okay, otherwise it cannot occur. And so I think this really nice. I mean, I suggest you can have if you are interested, you look at the original proof. The proof I will explain uses the Fourier transformation, and such an idea was also considered later also by Dubrovin and Guzzetti, but I will do a little differently. Use this idea.
Sorry, is it easy to say in words what are the Stokes matrices? What does it mean to Stokes matrix?
So we have recall that we have a differential equation in one variable. So we had with this connection. So lambda of T naught divided by Z plus A naught is the others. Okay. So it has a pole of order 2 near the origin, and there exists a gauge transformation, a formal gauge transformation, which changes this nabla knot into nabla knot hat, which is very similar to this one. So D plus lambda of T naught divided by Z plus the diagonal part is the other Z. So you see, this connection is very simple because this is diagonal and this is diagonal. So it's just a direct sum of rank 1 connections. So direct sum of rank 1 connections, you can solve very easily, find the horizontal sections. Okay. But this is only formal. This is only formal, meaning that if you really want to have a gauge transformation, holomorphic gauge transformation, in fact, it is not possible. So there exists holomorphic gauge transformations only in sectors at the origin. Okay, so you cannot find holomorphic gauge transformation all around the origin, but only in sectors. Now, if you the sectors are quite big, they are angle a little more than pi, okay, because the order of the pole is 2. The sectors are quite big, and you can compare what happens for one sector and for the other one. Okay, so there is 2 intersections for 2 sectors. One is bigger than pi, and the other one is also like this. So we can compare what happens in the intersection, and this gives two matrices that we call Stokes matrices to compare the different gauge transformations that you have here. Okay. So there are many choices, of course, but what we say that what they say that one can find such a choice where the entries, the IJ entries are vanish. These IJ.
Just a nice question. If you change the choice, it's no longer true in this case that like the.
Oh, you have to be careful. You have to be careful. Just to have to be careful. Yeah. Okay, so of course you can say what happens. Okay. So let me. What I would like to explain, or at least to give some hint of an explanation, is that in fact, the first part implies the second one. And this is quite amazing. So for the first part, it says exactly what I said here, namely the formal gauge transformation transforms your connection into a direct sum of rank 1 connections. So you have here a diagonal matrix and here a diagonal matrix. So you just consider rank 1 connections. It's a direct sum of them. But of course, this is only formal. Okay. But it does exist formally. So this first part, I will not give the proof. It is not so complicated, but it is quite clever that what they did. So I will accept this part. And what I am interested in is the second. Okay, so in order to understand what happens from the point of view of Fourier transformation, in this example, one can regard, so yes, Fourier transformation. So we have this connection here, the starting connection, nabla knot, which I do not write it once more. And the point is to, in some sense, to consider a Fourier or Laplace. Maybe Laplace would be a better name to that. Laplace transform and see what happens with the connection. So there is a nice way of expressing that, namely take a new variable lambda and essentially consider the Laplace kernel e to the minus lambda z, or something like plus or minus, I don't exactly know. Okay, so we want to transform solutions of nabla or horizontal section of this nabla knot into horizontal sections of a connection with respect to lambda. And so there is a way to do that, say algebraically. So without solving any differential equation, it's just to consider the connection with respect to lambda variable and with matrix D plus so the following matrix, let me write it. So A naught minus identity lambda of T naught. Let me see. No, sorry. Lambda identity minus lambda of T naught inverse d lambda. Okay, so this is a matrix which has poles with respect to lambda, pole of order 1. So lambda is a diagonal matrix. So you have a diagonal matrix here with 1 over lambda minus ti naught on the diagonal that you multiply by this one. So you find a connection with regular or logarithmic singularities at the points ti naught, I equals 1 to n. Okay, and in some sense, we want to play with this one instead of playing with the original one, in order that to have a nice correspondence, Fourier correspondence. well, one has to assume that the eigenvalues of A naught, say, are not integers, and of D naught, also the diagonal part, are not integers. And to do that, I mean, it's just simple. You add a constant. So replace A naught with A naught plus constant time identity for suitable complex numbers. So you will be sure that nothing is integer. And this does not change. I mean, you can add a D naught, replace D naught by D naught plus constant, and this does not change the problem. So this is not much a problem, and it makes easier understanding the Fourier correspondence.
Integers not equal to 0, or is integer zero more respect?
Not equal 0. Not non-zero. Okay. So now the result of Malgrange I wanted to state is the following. So we have this, let me call this one like Fourier f of nabla. So this new connection. So this is a connection with respect to the lambda variable. Our original connection was with respect to the z variable. So they correspond by this formula. And there is a result of Malgrange. So which will be a criterion for the vanishing of Stokes entries. So on the side of the lambda variable, the data we have are the topological data we have for this connection, because it has only regular singularities, are the usual monodromy data, okay? While on the other side, we had the monodromy data plus Stokes data. So here, we will play with monodromy data in this, on the Fourier lambda plane, lambda line. And the result of Malgrange says the following. And it was made maybe a little more explicit in a joint work with Daniolo, Marco Hin, Giovanni Morando, and myself. It says it gives so this gives an explicit formula. C'est topological. Let me insist. Topological formula for say S plus minus T naught, and more generally, but here, so the in terms of a suitable presentation of the monodromy data. I will not give the precise statement because I will not need really the precise statement, but just to say that we consider for the monodromy data of course, this Fourier Nabla maps. Okay, and explicit for this is for Nabla net. Okay. So one has to be a little precise of how to present the monodromy data for this connection. I will not be very precise here, but as a consequence of this explicit formula, the consequence is the following, that there exists let me, before the consequence, let me give some notation. So we have this connection, this Fourier connection, whose pole locus, you see the pole locus is lambda is at the points T naught. And so I call T, so the suitable presentation of monodromy data will lead to monodromy Ti around Ti naught. Okay. So we have a presentation of monodromy data by monodromy operators, monodromy matrices. Of course, one has to explain exactly how you present this monodromy matrix. Okay, and so the consequence of this precise formula is that we have the vanishing of an ij entry in general of this matrix, these matrices, occurs ij plus ji entry occurs if and only if the restriction Ti itself is not identity, but if I restrict to image of Tj minus identity, this should be identity. Okay. And same by exchanging I and j. Okay, so there is a very simple criterion in terms of monodromy data, ensuring that some entries of the Stokes matrix will vanish. Okay, so you can express this maybe in a simpler way, but let me just keep it like this. Okay. But so you remember the second part of the theorem of Cotti, Dubrovin and Guzzetti was a condition for the vanishing of entries, which is not like this. So the point is to relate these two conditions and check that this one, in fact, is implied by the condition of Cotti, Dubrovin, and Guzzetti. Okay, this one is quite general. Okay, so
sorry, by now, both guy J is distinct, right?
Yes, of course. They are always distinct. I mean, of course, you cannot expect a vanishing on the diagonal, because on the diagonal you have the diagonal of a Stokes matrices represent the formal monodromy, so it should be invertible. I mean. Okay. So usually in a pair of Stokes matrices, one is upper triangular and the other one is lower triangular. Okay. So the diagonal is always invertible. Okay. So we have two distinct conditions. One is saying that at least if you remember the first condition, the formal decomposition occurs all along the set of parameters, and it gives a decomposition into rank 1 bundles, formal decomposition into rank 1 bundles. And we have this one, which is quite different. And the point is how to relate both conditions. What is the relationship between both conditions? So let me interpret this condition as say something with parameters. So this is fixed at T naught, but we'd like to have some kind of dynamical interpretation of this condition. So to understand this condition, we now look at a little more at the geometry of the situation. So remember that we were considering a point, a coalescing point in delta, okay, with various corresponding to I1 up to IR, expressing how the coordinates are distributed, how they coincide or not. And let me consider in this, so we had this neighborhood we are interested in. And let me understand a little bit what happens with the hyperplanes. So we had the hyperplanes HI equals lambda minus TI equals 0 in the space of C lambda times U of TC. Okay, this is a trace of hyperplanes in this space. And so we can consider the union H of these hyperplanes. They do intersect. And when they intersect, so the singular locus of H, when they intersect, then when they intersect, at least one Ti equals to one Tj. Okay, so the singular set projects to delta in C in U of EC. Okay, because automatically when they intersect, at least two coordinates must be equal. But otherwise, so what happens in here? We have a point. Say, let me consider the point TC, and above this point, we have various. We have exactly R distinct points. Each one corresponding to IR. Okay, so here we have lambda 1 TC in the product with lambda 1 equals the value TC1 TCI with I in I1. All are the same. And so on. And here we have lambda R TC. We have R points. And in the neighborhood of each of these points, we have this union of hyperplanes. And if I focus to one of them, I see just the interesting ones corresponding to I1, say. Okay, so we have this geometric situation with some hyperplanes. So let me make a picture. So we have say fix k equals to 1. So let me consider the first point, for example, and so in the neighborhood of this point, so in the neighborhood of lambda 1 PC, what is the picture? So the picture is a kind of hyperplanes that intersect like this. Okay, so here is TC, lambda 1, sorry. And we have various hyperplanes that intersect corresponding to these values I. Okay? And we have a point T0, which is out of these hyperplanes, but it has the T0 I, say, the corresponding coordinates. It lies somewhere near this point, but out of these hyperplanes. And so the solution of our Fourier equation, we can deform it isomonodromically in the neighborhood of T0. And our assumption means that we can deform it up to all the upper planes and get a locally constant shift on the upper planes. So on the upper hyperplanes away from the intersections, so we have a locally constant shift. Okay, which is provided by, so Li provided by this Fourier there. And it's and it's isomonodromic deformation. So I'm going a little fast here because I lack of time, but just to say that we have a very natural local situation of a local system on each hyperplane provided by this differential equation here at T0. And now the point that it's like a proposition. This local system Li say on this can be represented by a vector space say the image of Ti minus identity. So we can represent a local system as a vector space plus monodromies. So, sorry, I will put it here. So at this point, the vector space is just the image of Ti minus identity, the one I had before, and monodromy around, say, Hj. So I have some Hj here. Sorry, yes, this one. So the monodromy around Hj of this local system is Tj acting on this vector space. Okay, so we interpret these monodromy matrices as defining local systems. And these local systems, in fact, are provided by the differential equation directly. And so you see that as a consequence of that, say just local geometrical analysis, a consequence of this consequence is that so Li is a constant local system, meaning that the monodromy matrices Tj on it are identity, implies, so for all I, implies that vanishing of Stokes entries. Ij, Ji in I of K for all K. Okay, so this vanishing, in fact, is provided. The vanishing is now provided by constancy of some local system. But this local system lives in the lambda variable, so in the Fourier variable. And to conclude, the conclusion now is that is obtained as follows. So condition 1 in the theorem of Cotti, Dubrovin and Guzzetti implies constancy of various local systems which were the formal, due to the formal expression at z equals 0. So if you remember, we had the direct sum of trivial local system at z equals 0. And by a theorem that I had proved long time ago with Antoine Doué, which is in fact a stationary phase formula. With parameter. So by this stationary phase formula, these local systems are exactly, these are the Li. These local systems are the I's which are just constant. So the Li's are constants. So this is a stationary phase formula which compares two kinds of local systems, one obtained by this formal expression and the other one by what we call sheaves of vanishing cycles. Okay, so at the end, this condition implies that these local systems are constant. And by what I have said before, this implies that the criterion of Malgrange is satisfied. So I will stop here. Sorry for.
Any questions, comments?
You try your life way.
And so the result with Douai, we would say the following. If you apply, say, inverse Fourier transformation, so we have a connection here which is defined in some neighborhood of T naught. So here I just considered T naught, but also in some neighborhood of T naught. And we have a connection, and we consider the local system consisting of vanishing cycles of the underlying D module. Where we have a regular holonomic D module. It's the RAM complex, and we consider the vanishing cycles along, say, each HI. Okay, so these vanishing cycles are local system on some open subset of HI away from the singularities. And whatever the local system is, we know that after Fourier transformation, this local system will occur as one local system in the formal decomposition at infinity, at c equals 0, formal decomposition. Okay, so we have a one-one correspondence between these two kinds of local systems. So why is it the stationary phase formula with parameter? If you fix T naught, it just says that the vanishing cycles of your D module at some singular point lambda equals T naught sub I, then the vanishing cycles reflect the exponential behavior at infinity. So so this here we vary T naught, so we have a local system, not just a number. Okay, just that's okay. So this is just a variant of the stationary phase formula.
Can you interpret the conjunction on the side of Nabla L with the monodromic Ti with respect to the braid group action on the monodromism?
Yes, yes. I mean, you could do that. This is why you need a choice, a precise choice, not to be lost in the braid group action. Otherwise, I mean, you have to be careful with conjugacy of.
Like the joint of the exchange I and J arms on the.
No, but
that should be kind of related to this condition, or maybe that's not exactly.
No, it's not exactly. I mean, the point is that the braid group action will act really. I mean, will change, but the point is to have a concrete choice of representatives of the monodromies, and so we usually we have the various points T naught I on the plane, lambda plane. So we fix some direction, some half direction to be sure to fix some data, and everything is done with respect to these half directions. Now, this choice of half direction will make influence on the Stokes matrices, because for Stokes matrices, you only need to choose directions. Okay, so this is. Okay, so.
Quick question or quick comment? Well, actually I have several questions, but maybe in the next days I will ask you direct. So if no other comments arise, let's thank the speaker again.